Hi dear students. So let us discuss the equilibrium of a rigid body. So there are two types of equilibriums. One it is linear equilibrium or translational equilibrium, and another one it is the rotational equilibrium. So a rigid body can be either in rotational or in the translational equilibrium, and as well the same way both the translational and as well the rotational equilibriums can perform by the obtained by a rigid body. If the total linear force acting upon the rigid body, if it is zero, then we can say that is the body is in the translational or linear equilibrium. That is, suppose n various forces are acting upon the rigid body. Suppose if you are having a particle, n number of particles, and on each particle various forces. So F1 for the first particle, F2 for the second particle, likewise Fn for the nth particle. Then the sum of these all forces should be 0. That is F1 plus F2 plus etc. up to Fn should be 0. That is in terms of summation, you can write that one as summation of I is equal to 1 to n. Fi is equal to 0. This is the condition for the linear equilibrium. So linear equilibrium in the sense the force acting upon the particle, the various amount of or individual, the sum of the individual forces acting upon particles in a system should be 0. Then we can say the particle is in the linear equilibrium. Likewise, in the case of the rotational equilibrium, the analog of the force in rotational motion, that is the torque. So individual torque acting upon the particles of a rigid body which is in rotational motion should be the sum of that torque values for individual particles should be 0, or we can say the sum of the total or net torque should be 0. Then we can say that particular body or rigid body or system of the particle is in the rotational equilibrium. So if both the equilibriums are there, if a body is having both the equilibriums, linear and as well the rotational, or translational and as well the rotational, then we can say the body is in the mechanical equilibrium. Suppose if the body is not in rotational equilibrium but it is having the linear equilibrium, or else if it is having the rotational equilibrium but not the linear equilibrium, then we can say that the body is in the partial equilibrium. Okay. So for the mechanical equilibrium, the sum of the components of the force along two perpendicular axes and the plane must be the sum of the forces acting upon that body should be 0. One thing, if all the forces acting on the body are coplanar, that means all are acting in the same plane, then we need only 3 conditions to satisfy the mechanical equilibrium. If the forces acting upon a body, if it is coplanar, in the same plane if it is, then we need 3 conditions. The conditions are, 2 of them are corresponding to the translational equilibrium and one it is for the rotational equilibrium. The sum of the components of the forces along any two perpendicular axes in the plane must be 0. If the force acting, if it is coplanar, then the sum of the for the condition of the, if the force is acting upon a body, if it is coplanar, then the condition for obtaining the mechanical equilibrium, the first one it is the sum of the components of the forces along any two perpendicular axes. That means suppose if you are considering a y-axis, the force on the along y-axis, and the sum of the force along x-axis or the z-axis. Okay, means y, the force along y plus force along z, or force along y plus force along x. That should be 0. And the next condition is regarding the rotational equilibrium. Same, that is the sum of the components of the torque acting along the perpendicular axis to the plane of the force must be 0. So any of the axis which is perpendicular to the plane, the torque acting upon that plane means the forces. We are considering the forces, the two forces, and the two forces should be lying in a plane. And the value of the torque which is acting perpendicular to that plane should be 0. Then we can say the body is in the mechanical equilibrium. That is, both the linear and translational equilibriums are already obtained by that body. Now regarding the partial equilibrium, just observe the first figure. You can see the linear forces, both the forces are acting downwards. That means the direction of the force is same only. Suppose if the force value, if it is same for each f, if it is equal force at A and B, if you are applying the same amount of force and both are acting downwards, that means linearly the equilibrium is not obtained because both are in the same direction. But you can observe regarding the torque, you can observe one of the torque value it is acting clockwise and in another one it is in the anti-clockwise direction. So equal and opposite directions. So the torque value here will be, the net torque value will be 0. But at that time net force it is not 0. So this body is in rotational equilibrium but not in the linear or the translational equilibrium. Okay. Same way here, the forces at A and B are acting opposite. One it is acting downwards, another one it is acting upwards. So linearly and equal and opposite. So the net force value will be 0 here in this case. So linear equilibrium it is obtained. But regarding the rotational equilibrium, you can see the torque value, you can see here it is acting anti-clockwise, here also anti-clockwise. So the net torque value cannot be 0. Hence the body cannot be in the rotational equilibrium. So the first figure representing a linear equilibrium, and the second one it is representing a pure rotation. First one it is indicating the rotational equilibrium, and the second one it is representing linear equilibrium. So here both the equilibriums are not occurred togetherly. So these equilibriums are known as the partial equilibrium. Okay, either the rotational or the linear. So such equilibriums are known as the partial equilibriums. Now let us come to the term that is couple or torque. If a pair of force of equal magnitude, so the value of the force it is same, the magnitude of the force it is same, and acting in opposite direction with different lines of action. So you can, with the representation is here, opening a top of the lid of the bottle. So here the force acting, here it is in this direction, here it is direction. The amount of the force you are applying it is same and they are in the opposite direction. The line of action is opposite. It means it is forming a pure rotational motion, and that force, rotational force, that is known as the torque, and this condition it is known as the couple of forces, two couples. One it is this one, the one couple, one it is this one, another one is this one. So the couple of forces, two forces, they are equal and opposite, and they can produce a pure rotational motion, and such forces are known as couple or a torque. So the couple can produce a pure rotation without the translational. There would not be any linear movement. Only the rotational motion can occur by a couple or a torque. Okay. Now come to the principle of moments. So here an arm it is given or a rod it is given and it is pivoted at one point, that is O. So scientifically it is known as the fulcrum. And two forces at the ends A and B, two forces are acting. One it is F1 and another one it is F2. The distance from the fulcrum to B it is D2 and from fulcrum to A it is D1. So here an R it is given, that is the reacting force, that is the normal force. Okay. So for the translational equilibrium, all the forces acting upon this point O should be zero, linear forces. Here three linear forces are there. One it is the R, another one F1 and the last one F2. So here R, F1 and F2 both are acting in the same direction, and R is acting in the opposite direction of F1 and F2. So if you are considering the vectors, taking the sum, the R plus minus F1 plus minus F2 will be there. So because they are in the opposite direction of R. So the total sum of the linear force will be R minus F1 minus F2 will be equal to 0. Actually that is R plus minus F1 plus minus F2. Okay. So the total linear force for equilibrium, translational equilibrium, the total linear force, the net linear force value should be 0. Hence R minus F1 minus F2 should be equal to 0. Now come to the rotational equilibrium. So for the rotational equilibrium, the torque values, the net torque value should be 0. Here if you are considering the end A, you can see the force acting it is F1 and the radius of gyration or radius of rotation, it is D1. So the torque value, if it is at that point A, it is D1 F1, and the same way at the end B it is D2 F2. Okay. So the sum, both are acting in the opposite direction. So D1 F1 plus minus of D2 F2 should be 0. One it is clockwise and another one it is anti-clockwise. So anti-clockwise one should be taken as positive and the clockwise one it is taken as negative here. So here the point O or the R is acting as a fulcrum. So the zero moment will be there at the fulcrum. It means the torque value at R will be 0 because it is at the center. Otherwise we can say the radius of gyration at the center will be 0. Hence the torque at the center should be 0. So the moment of force of R should be 0. Now you can consider this portion OA portion as the load arm, because you are applying some load over here, that is the force F1 is actually the load. Then this one, that is the D2 distance, it is known as, that portion it is known as the effort arm, and the F2 is the effort that you have applied to balance this F1. Okay, you have already studied those things in the lower classes. So the relation it is there, one relation it is there, that is F1 into D1 will be equal to D2 into F2. That is load into load arm is equal to effort into the effort arm. Okay. So D1 F1 is equal to D2 F2. Load arm into load is equal to effort arm into effort arm. This one particular term you have to study, that is the mechanical advantage. Mechanical advantage is actually the load divided by the effort. That is F1 divided by F2. F1 divided by F2. So from this relation, that is D1 F1 is equal to D2 F2, you can find the mechanical advantage MA value in terms of the distance, load arm distance, and as well the effort arm distance as d2 by d1. That is f1 d1 is equal to f2 d2. So f1 by f2 is equal to d2 by d1. So this is the mechanical advantage. Okay. So if the load is more, then the mechanical advantage value will be, that is if f1 is greater than f2, that is the load value, if it is more, then the mechanical advantage value, that is MA value, will be greater than 1. If the load it is less, that is F1 is less than F2, F1 is the load and F2 is the effort, then the mechanical advantage value will be less than 1. Okay. If the load is more, mechanical advantage value will be, or if the load is greater than the effort, then the mechanical advantage value will be greater than 1. And as well, if the load it is less than the effort value, effort you have applied, then the mechanical advantage value will be less than 1. Okay. Now come to the center of gravity. Actually, you can relate the center of gravity with the center of mass. Actually, center of mass is the point at which the mass of the system is concentrated. Here in this case of the center of gravity, the point at which the weight of the body it is concentrated. So mass and weight, if you are comparing the mass and weight, you know that mass into the gravitational acceleration value is actually the weight. So if you are considering a point at which the distribution of the gravitational acceleration throughout the system, or throughout the system of that particles, if it is uniform, means the value of g it is equal throughout the body, then the center of mass point and the center of gravity point should be coincide. If that is not uniform, then the center of mass point will be another one, and the center of gravity point should be another one. They are different. They will become various. Various points will be there, as the gravitational center the center of gravity point will be there, as well the center of mass point will be there. If the gravitational acceleration value, if it is uniform throughout the body, then both the center of the mass and as well the center of gravity coincide. And suppose if you are considering a particle where Ri is the position vector of the particle with respect to the center of gravity, then the torque about the center of gravity will be, suppose the particle is having a mass mi, and the torque value will be tau I, which is equal to Ri cross mi into g, where mi into g is the weight, which is linear force. So that linear force into the radius of gyration, or the radius of rotation, that is Ri, or that means the position vector of the particle with the center as a center of gravity. So Ri, so tau I value will be is equal to Ri cross mi into g. So the total gravitational torque about the center of gravity is 0. The total gravitational torque about the center of gravity is 0, because the axis should be, we consider the axis as the center of gravity, the axis which is passing through the center of gravity, then the torque along that point will be 0. So summation of Ri cross mi into g will be 0. Okay, so summation of Ri cross mi g will be 0, where g cannot be 0. G cannot be 0. Then Ri cross mi will become 0. Now you know that the center of mass value is equal to, or the point at which the center of mass concentrated is actually summation of mi Ri divided by summation of mi. Now we have seen the summation of mi Ri is 0. That means at that point the center of mass will be lying at the origin. Here in this case we have considered the origin as the center of gravity. Okay, here we have considered, that means the Ri, the position vector we have taken from the center of gravity. Center of gravity was the, with respect to center of gravity it is given. That means center of gravity is considered as the origin here. And if the net torque value, the gravitational torque acting, if it is 0, then the center of mass will be lying at the origin. That means here you are considering the center of gravity as the origin. So center of mass and the center of gravity should be coincides together. Okay. Now comes to the important portion, that is the moment of inertia. Simply, the moment of inertia is the analog of mass in the rotational motion, and it is denoted by I, the letter I. So the torque is actually the analog of the force, and as well angular momentum is there, L, that is actually the analog of the P in the case of the linear motion. Likewise, you have already studied the inertia. Inertia in the linear motion, you have studied the inertia. That is the inability of a body to change its state by itself. That means if a body, if it is in a uniform motion, it will be continue that motion until an external force acting upon it as well. If a body, if it is at rest, it will continue on that state until a force acting upon it. So that is the inertia, and that is inability. That inability, it is the inertia in the case of linear motion. So here also the moment of inertia is also the same here in the case of the rotational motion. Okay, the same concept, but the motion it is not linear. Here it is a rotational motion. So the moment of inertia. And now we can compare, actually tau is actually for the rotational motion, tau is for the EF in the linear motion. Likewise here the inertia, it is representing one time. So which time it is, we have to find that one. So for that purpose we have considered the linear velocity Vi as Ri into omega. That equation we have already studied. Vi, linear velocity Vi is equal to Ri into omega. We are considering a one particle which is at the ith position, or ith particle, nth particle, likewise ith particle. For its linear velocity value, it is Ri into the omega. Simply V is equal to R omega. So for that particular body, the kinetic energy, the linear kinetic energy value, it is there. Likewise, the linear kinetic energy value will be Ki is equal to half of Mi into Vi square, that is half into Mv square. Okay, so Mi, it is representing the mass of that particular particle. So now you have to rewrite or rearrange the V in terms of R and omega. That is V, you have changing, so V square, that is Ri into omega the whole square. That is the kinetic energy value will become half of Mi into Ri square omega square. Now this is just for one particle. Now if you are considering the entire numbers of the particle, then you have to do the summation. So the total kinetic energy value will be summation of I is equal to 1 to n Ki, that is half of I is equal to 1 to n Mi into Ri square omega square, where omega it is constant. For all the particles, the angular velocity will be constant. So omega you can take outside. So that will become K into half of omega square summation of I is equal to 1 to n Mi Ri the whole square. where this mi into ri square is known as the moment of the inertia. So mi into ri square is the moment of the inertia. So that is represented by I. Now we can rewrite this one as, that is summation of I is equal to 1 to n mi into ri square. You can take that one as the I. Then the equation will become k is equal to half of I into omega square. So now you can compare this k is equal to half into I omega square, and as well the ki as half into m into v square, where you can see half, then v square, that is the linear velocity, omega square, that is the angular velocity. So I, it is representing the mass in the case of the linear motion. The linear motion, mass, angular motion, inertia. So we can say moment of inertia I is actually the analog of mass in case of rotational motion. So here this I, it is independent of the magnitude of the angular velocity. I, it is not depending upon the magnitude of angular velocity, and it is repeating only upon the mass and the position vector. Means through which axis it is rotating. So it is representing, or it is an inertia is depending, or we can say it is the characteristic of a rigid body and the axis about which it is rotating. Rigid body is characteristic in the sense of the mass of that particle or mass of that body, and this Ri representing the axis of the rotation, on which axis it is, on the basis of which axis it is rotating, or the rotation on the basis of which axis we are considering. Okay. So we can see, if you are considering the equation k is equal to half mv square, where m is the mass of the body and v is the velocity. Likewise, in the angular kinetic energy, if you are considering the angular kinetic energy, where chi is equal to half into I omega square. So we can say omega and v, omega square and v square, that are analogues, and then I, the moment of inertia, is the analog of mass. Okay. Now let us come to this figure. We have to find out the moment of inertia at the point C. Okay. So equation to finding out the moment of inertia we have already studied. We have seen, that is m into r I the square, ri square. That is the moment of inertia value. Here we are having a rod of total length L. The total length it is L. So the point of rotation it is at a C. So the R values will be L by 2, and the mass values are given, that is both the ends m by 2 mass it is suspended. So you have to find out initially is a total net moment of inertia you have to find. That is, initially you have to find out the moment of inertia along this axis or for this body, and afterwards you have to find out the moment of inertia along this axis for this particular body, and you have to add up that. So in both the cases the value it is same only, because mass it is same, then distance or the position vector it is also same. So you have to just take the double, or you have to just multiply it with 2. It's okay, otherwise we will find it independently. First one, for this first body, mass into the radius square, that is m by 2 into L by 2 the whole square, plus for the second body same m by 2 into L by 2 the square. So for this pair of masses rotating about the axis through the center of mass, here this point it is actually the center of mass. Okay, and the axis of rotation, it is perpendicular to the axis which is on which it is aligned. Okay, otherwise we can say the rotating about the axis through the center of mass perpendicular to the rod. Okay, the axis of rotation, it is perpendicular to the rod. This is the rod and this is the axis of rotation. So they are both are perpendicular to each other. So the moment of inertia through the axis which is perpendicular to the rod will be is equal to m by 2 into L by 2 all square plus m by 2 into L by 2 square, that is m L square by 4, the moment of inertia value through this axis which is perpendicular to the rod. Okay, this is the way you have to use to find out the moment of inertia values. If any in the examination, if it is asked, you can use up this equation. Likewise, suppose if you are given with like this, if you are given here m mass, it is subtended, here if it is m by 2 is subtended, and here the distance it is L by 3, and here it is 2L by 3. Then if you want to find out the moment of inertia through the axis which is perpendicular to the rod, then m into L by 3 the whole square plus m by 2 into 2L by 3. Okay, I'm not writing here, I'll write here. Okay, m by 2 into 2L by 3 the whole square. Such a way you have to find out the moment of inertia value through the axis which is perpendicular to the rod here in this case. And if it is given that it is passing through the center of mass, means if both the masses are equal, then the exact center point you have to consider. L means if total length, if it is L, then L by 2 distances will be there. Okay, otherwise if it is not mentioned, then you have to find out the center of mass first of all. Okay, so the deposition vectors of the various masses also will be available. With the help of that one, you have to find out the center of mass points, and then you have to find out the moment of inertia value. Okay, now for some particular bodies or for some particular structures, the moment of inertia values along the axis which is perpendicular to the plane and as well parallel to the plane, likewise it is given. So first one, it is a circular ring, and the axis of rotation, it is perpendicular to the which is passing through the center of mass and which is perpendicular to the plane. So the value, it is mr square. And now the axis of rotation is along the diameter of that ring. It means it is parallel to the plane. There the value of inertia, the moment of inertia value along that axis is mr square by 2. Thereafter it is given a rod, a thin rod. There is a value of, and the axis, it is perpendicular to the rod at midpoint. The axis of rotation, it is passing through the midpoint and it is perpendicular to the rod. There the value of it is, that is m L square divided by 12. ml square divided by 12. Now one circular disc is given. For that one, first of all you are considering the axis which is perpendicular to the plane of the disc and it is passing through the center, where the moment of inertia value, it is mr square by 2. And thereafter the axis we are considering through the diameter, then the moment of inertia value through that axis will be mr square by 4. Thereafter a hollow cylinder and as well a solid cylinder. Both cylinders are given. For the hollow cylinder, it is same as like that of the circular ring, and that is mr square. And for the solid cylinder, it is like a disc. For the disc, whichever the value it is, the same will be there, that is mr square by 2. For the disk, the axis should be through the perpendicular. That case you have to consider. You can compare these things and study. And next one, a solid sphere, and the axis of rotation is through the diameter. There the value of moment of inertia is 2 into mr square by 5. These values are important for doing the calculations and all. So go through this table and as well thorough with these values. Compare these things and study. Then it will be easy. Okay. So now there are some theorems that we will discuss in the coming section. So this much things you just read from the textbook. Read this much portion from the textbook today itself. That will be more helpful. You can understand little bit more if you are going through the by yourself, if you are going through the textbook. Okay. So thank you.